Hi everyone, this is Emmanuel from AirTrain. So today I want to talk about a plot that I found online. It was published back in May on Twitter by Andrej Karpathy. Andrej Karpathy is one of the founding engineers of OpenAI, went on to work at Tesla then and back at OpenAI now. And the plot essentially explains the various techniques you can use to improve the performance of an LLM. So I want to go over some of those techniques and see the ones that are easily applicable by you today and the ones that may need a bit more work. So here's the plot. You can find it on Andrej's Twitter account. And so the x-axis here is the effort that you need to apply to sort of use those techniques. And on the y-axis here, you can see the task accuracy the accuracy of a particular that the model will have for a particular task. And so you can see a blue line and a red line. The red line is for small base model, and the blue one is for big base model. So big base model typically is, let's say, I mean, it's obviously arguable, but above like 1 billion parameter, for example. So the first area you see here on the left, so it's probably the easiest way to improve the performance of your model is to do prompt engineering. I'm sure you know prompt engineering is trying different variants and different shapes of your prompt, changing the language, changing the wording that you use in your prompt to get the model to respond better. So you can maybe use your user's inputs, so the user prompt, and then wrap it in your own prompt to make sure that the model understands what you're trying to do. So as you can see on this plot, this will get you quite a bit of the way there already. You can already get some pretty good results when it comes to big base models. Now, the next thing you can do to improve your model performance is what they call few-shot prompts. So maybe you've heard about this few-shot learning. The idea behind few-shot prompts is that inside your prompt, you are teaching the model what is a good answer for the question and what is a bad answer for the question. So as part of your prompts, you're sort of giving your model a guidance, a sort of guidelines as to how you want the model to respond. So, for example, here's a very dumb example I came up with in GPT-4. So the first prompt that I asked is, what is a good name for a store that sells turtle? So this is zero-shot learning. There's just a single prompt, really dumb. And so GPT-4 comes up with a list of names. Some of them are pretty good, some of them are bad. So how do I guide GPT-4 to know which prompts are good and bad? So this is what they call few-shot learning. So essentially, as part of your prompt, you have to give examples of what are good answers and examples of what are bad answers. So I rewrote the prompt with I am looking for a name for a shop that sells turtles, and here's a list, example of names that I do not like, the Lame Turtle Shop, and so on. And here are some names that I like, Tools R Us, Slow Mo Ninjas, and so on. And so the model, so GPT-4 in this case, understands what is good for me and what is bad on my own grading scale, if you will, and will output names that are more in tune with the examples that I gave. Obviously, this is a very dumb, basic example, but you get the idea. You essentially have to wrap your prompt into a list of examples of things that work well. So it could be, question answers or classifying different responses to teach the model how to get better. So as you can see on the plot, obviously this is not a scientific plot. This is just a schematic plot that was drawn by Andrej. These are not real numbers. But essentially, this is the next thing you can do on top of prompt engineering. So the nice thing about this technique is that it doesn't cost much more for you. You don't need to host your own model or fine tune or do anything crazy with it. You can basically add those things to your prompt, and that's it. You will get better results. So that's kind of a cheap way of getting better results for your model. Now, after that, the next step is to do what they call RAG. So RAG means retrieval augmented generation. So this is more difficult to put in practice because you need to build a system around the model. You need to have a query engine, a vector database, and so on. So the idea behind retrieval augmented generation is that first, the idea is that you can get your model to respond to the question with data that the model has not seen before. So for example, if you're trying to develop a chatbot that will answer a question based on some private knowledge base that maybe your company has, so maybe your private wiki, for example, or anything that is not really available to the model, or that is not the model has not been trained on, then you will ingest all this data in what they call a vector database. So we'll do another video on that, but essentially a vector database converts a piece of text into a set of numbers and a vector, and you can use this to do what they call similarity search. So finding two documents that are similar in content, or finding a set of documents that are close to what the question of the user is. So this is what retrieval augmentation generation is. The user will ask a question. You will use this question. You will transform this question into a vector. You will find the top n documents in your vector database that correspond to this question. So it's very much like a search engine, if you will. It's like Google, you add a question and you get maybe the top 10, top 20 answers. So it's the same as your wiki search. And then you pass this content, so this top n documents, inside the prompt. So you add the content of the document inside the prompt alongside the user's question. And at the end, you ask the model to extract a response for an answer for that question from those documents. So obviously there's a lot of complication there, because first of all, you need to ingest your document into a vector database. It means you need to host a vector database or pay for one. There's tons of options out there, Pinecone, ChromeDB, and so on. So that's already a lot of work. Then you need to make sure that you work with a model that has a large enough context window. The context window is the size, the number of tokens that a model can take as an input. So obviously, if you want to feed 10 or 20 documents in your context, you need a large context window. So some models out there are very large context windows, like 50K or 100K tokens. So that can actually work with RAG. And so once you pass this prompt to the model will extract the answer to the question from this private data. So the really nice thing about RAG is that you can actually have models answer questions about private data without having to train the model on this private data. So it's quite powerful, but again, it needs a bit of work to get to work. And so that gets you some of the way there in terms of accuracy. And then the biggest thing that you can do in terms of effort and complexity is fine-tuning. So fine-tuning is quite difficult. You need to have your own sort of training pipelines and fine-tune the model with your own data. So that's a lot of compute, a lot of sort of skills to have. So you have APIs out there to do that. OpenAI has a fine-tuning API for GPT-4. I think also Anyscale has a fine-tuning API, but that's kind of a really hard thing to do, and so it's really not recommended as a first step to get your model to perform better. So as you can see in this plot, really you can get a lot of improvement in your model by not building any infrastructure or any tooling around your model, by just engineering your prompt and then using few-shot prompting. And for the rest, you would have to talk to your engineering team to build those RAG and fine-tuning system. So yeah, this video was really just about showing this plot that really was kind of enlightening to me, and I hope you enjoyed it. So check us out at airtrain.ai. We provide evaluation and fine-tuning as a platform. And yeah, that's it for today. Thanks. Bye-bye.